The bell work, what we have to do is we have to recognize the antiderivative for 2t cubed. So if 2t cubed is our little f of x, then our antiderivative, big F of x, is got to be something to the fourth power. And then we need to have a coefficient out here so that we end up with a 2 when we do the derivative on this and bring down the 4. So the coefficient out here must be 1/2. So if we look at big F of x, taking its derivative, we end up with bringing down the 4. 4 times 1/2 gives us a 2. Reducing the power then by 1 is a power of 3. So to evaluate this, then we're going to evaluate the antiderivative at 2 and subtract the value of the antiderivative at -1. So the antiderivative at 2 is 1/2 2 to the fourth minus 1/2 -1 to the fourth. And 2 to the fourth is 16, half of 16 is 8, and this is 1, so it's 1/2 times 1 is 1/2. So the value of the antiderivative from -1 to 2 of 2t cubed dt must equal 7.5. So as we're looking at the fundamental theorem of calculus, we're looking at just this process that we had above here, where we're identifying an antiderivative, and then we're evaluating that antiderivative at the upper and the lower bound. So let's take a look at how to do this using some technology, now that we know how to do it without technology. So looking at this using technology, right here we have the derivative f of x. So this is the derivative. And so we've graphed that derivative f of x. And then if we want to graph the antiderivative, we can put that right in the y2 equation, or the y2 graph. And so what this is saying is this is the antiderivative, and this is the it's not necessarily a lower bound, but we'll call it a lower bound. Really, the important thing is this upper bound is basically telling you to graph it for all values of x. And so on the newer calculator it looks like that. On the older calculator, the f int looks like this. But then the same thing, here's our y1, which is our derivative function, differentiable variable 0, or x, and then lower bound of 0, upper bound of all x's. And so as we graph that, then that looks like, putting that into the calculator, looks something like this. So clearing out that, we've got 2x cubed, and then going down to y2, we go to our math button, and we go down to option 9, f int. So we click option 9, and then we can go ahead and type in 0, arrow up, variable x, and then over into the derivative box, and we grab the y1 graph by using our vars key, and then we arrow right to y-vars and select function, and then we select y1, and then we can come over and stick our variable x in there. And then as we graph this, it looks like there's the derivative 2x cubed, and then it takes a while to generate the antiderivative, so that's going to take a little while, but here it comes. So it's calculating the antiderivative for all values of x and plotting that for us. And so this is an x to the fourth power polynomial, and that looks something like, as it eventually graphs, looks something like that. And so what we can do once we have this graphed, so we'll let that graph finish up. We're going to come back to that in just a second. So after we let that graph, we're going to look at that and calculate the actual value of the definite integral from the value of the definite integral from a lower bound of -1 to an upper bound of 2. And we're going to do that right in our graphing function using our second calc. So if we look at that, then we're going to go to second key and calc, which is basically your trace key. And we're going to do an integral, so option 7. And our lower limit here is going to be -1. And our upper limit is going to be 2. And you can see we've evaluated then the integral of 2x cubed from -1 to 2. We've calculated the area under that graph. So we're going to take that and put that into here. Okay, and so we have then these two regions of area calculated. And so if we notice that this region here is an area of 1/2, and it's beneath the axis, which is why we ended up subtracting it. And then this region here has an area of 8. And so when we subtract the two, we get the value of the definite integral, which is 7.5. That's the 8 minus 1/2, since that half region is beneath the x-axis. And that's what gets us our 7.5 or 7.5. If we look at the table, so looking at the table here, we can see in this table that y1 is the derivative, y2 is the antiderivative. So we can literally see the values of our antiderivative right in this table. So let me just grab the table here, and we'll put it right in here. And so as we look at this table, we can see that we have the y1, which is the 2x cubed, and then we have the y2, which is the integral of 2x cubed dx. And so if we look at -1 in the table and we look at 2 in the table, we can see those values of those integrals. So here's -1 in the table. We have 0.5 as the value of the integral. And here is 2 in the table, and we have 8. So we can see that looking right at the table as well as looking at the graph. So knowing that, then if we go from -1 to 0, we know that this will give us a value of -1/2. And then when we go from 0 to 2, we're going to have a value of 8. We can see that right in the table, or we can see that using our calc int. And so we can see then that that when we have an integral that goes from -1 to 2 of 2t dt cubed, that gets us our 8 minus 1/2 which ends up being our 7.5. Now, that is the definite integral. The other question we could ask is what happens if we want to talk about the area. And so when we talk about the area, we're really talking about that absolute value amount. So when we're talking about that, then since -1 to 0 of 2t cubed dt is negative, we're going to take the absolute value of that and add to it from 0 to 2 of 2t cubed dt. And so this is going to be the absolute value of -1/2 plus 8. So the total area, like if I were to paint this, and we would need to know how much paint we would need, the total area in geometric terms is 8.5. You can also calculate integrals from your main screen on your calculator. So we're going to go through that too with this function as well. You don't have to go to the graph screen. So, and I'm going to show you calculating the integral and then also doing the area. So we're also going to look at those two things and show you how to do this really quickly with a graphing calculator. And this is a huge time saver on the AP exam. So you'll definitely want to do this, use this technique if you run into these type of problems on the AP exam in the calculator part. So if we go back to our calculator and go back to our main screen, we can see that under the math key we have an fint function 9, and we're just going to go ahead and put in -1 to 2, and go ahead and we can do one of two things. We know the function's in y1, so we can grab y1 out of vars, or we can just go ahead and say 2x cubed and put in the whole function and then dx. And so when we hit enter, then we get that 7.5 for our area. Also, we can do the for the definite integral. We can also do the area though, and this is kind of a nice function, a nice capability is we can go back into fint and go from -1 to 2, and if we want the area, if we want the area between the curve and the x-axis where we want to treat everything as positive, we can go back into math and arrow to the right under number and grab option 1 here, which is the absolute value, and we can just stick in the absolute value. And if you can see we have absolute value symbols up here now. 2x cubed dx. And as you can see, now we get the answer of 8.5, as if we made every region from -1 to 2 a positive region. So we have the capability of doing both a definite integral and a total area calculation really quickly. So here are here's the syntax to put in to do each one of these things if you want to do the area or the total area, or the definite integral or the total area, real quickly just from the calculator home screen if graphing it is not important. So when we're talking about doing an area calculation, we're really saying let's take the absolute value of the function 2x cubed. And so if here is the function 2x cubed, so this is 2x cubed, what does the absolute value of that look like? Well, we know that where it's already positive, it's going to continue to be positive. So in this portion, we still get that. But then this portion also turns positive. So we have this and then going up in that direction. So here's the absolute value of 2x cubed. And then we can see that we get this region here, this negative, what used to be -1/2, now be +1/2. And then this region here which was that region of 8, continue to be a region of 8. I want to get into what happens if we start kind of modifying these upper and lower bounds here. So here's what we originally started with, this antiderivative that we've been talking about for the last 2 pages ends up being 7.5. So how would this change if we took the top upper bound and replaced it with an x? So now we're looking at evaluating this at x. And subtracting the value of that antiderivative at 1. And so we know that the antiderivative is 1/2 t to the 4th. And so if we put in an x, we have 1/2 x to the 4th minus 1/2 negative 1 to the 4th. And so we end up having 1/2 x to the 4th minus, and evaluating this, we get 1/2. So really kind of what we're saying here is we're starting this accumulation of regions at -1. So here's -1. And we start the accumulation of this region, and we're just going to keep going out to some random location x. And so really it's kind of saying here that we can start at x equals -1, and we can accumulate to the right however long we want to. So that's kind of what we're saying there. But this is kind of where they take this. They say, well, okay, that's all fine and good. We evaluated this antiderivative from -1 to some random location x. But what if, after getting that result, we ended up taking the derivative of what we just got? So now we end up taking the derivative of 2x to the 4th minus 1/2. And that derivative ends up being 2x cubed. And so if we notice, basically what we did is we just took the derivative of an antiderivative. And we know that taking the derivative and finding the antiderivative are processes that kind of reverse each other or undo each other. So hopefully it's not too much of a surprise to realize that we ended up going right back to where we started. The only difference is that instead of having a t as the variable, we have an x as the variable, but it looks just the same as the function that we started with. So we call this the Fundamental Theorem of Calculus, Part 1, and a lot of people call it the plop rule. And that is basically if we have an indefinite integral with a constant value as the lower bound and an x as the upper bound, then whatever we have as the derivative, if we end up taking the derivative of that antiderivative, we can just plop in the x. And that's what we end up with. And so that is the Fundamental Theorem of Calculus, Part 1. So if we look on this next page here, that's kind of what this says here. We're taking the derivative of the antiderivative, and so we're ending up just with the derivative function. We end right back up with that same function, but with x in there instead. So using this Fundamental Theorem of Calculus, Part 1, let's take a look at a couple of examples here. We notice that we have a constant and the variable x. And we're asked then to take the function cosine of t, find its antiderivative, and then its derivative again. So we know that the answer here is just cosine of x. And likewise, same pattern here. We got a constant down here for the lower bound. We've got the variable x. And so this is a function. Now, the cosine of t, you probably would be able to find the antiderivative for, but 1 over 1 plus t squared, we won't know how to find the derivative of that until the next chapter. But since all we're being asked to do is find the antiderivative and then take the derivative of that, we know we end up right back where we started. So we know that this is just 1 plus x squared. What we're going to do is we're going to look at how we can apply the fundamental theorem of calculus, part 1, to when we have the variable in the lower bound and a constant in the upper bound. And so we're going to go back to the function we know so that we can kind of do this quickly. So we know that the antiderivative here is 1/2 t to the 4th. And so we're going to go ahead and evaluate that antiderivative at 2 minus the value of the antiderivative at x. And so when we evaluate that, we have 1/2 2 to the 4th power, evaluating the antiderivative at 2. And then evaluating the antiderivative at x gives us this. So this ends up being 8, and this ends up being the function 1/2 x to the 4th. So if we would then take the derivative of what we just found, so what we just found is the antiderivative of 2t cubed dt. That would be like taking the derivative of this, 8 minus 1/2 x to the 4th. And so differentiating that, we get 2x cubed, but we have a negative out front. So if you notice, we can still really just plop in the x. We did start back where we did end up back where we started, but since the x was in the lower bound, so if we have something that looks like this with a constant, so since the x was in the lower bound, we end up then with a opposite of the value of that derivative. Since this is just a constant up here, differentiating the constant 8 makes that go away. So we end up just gaining a negative sign there. But still, we can just kind of plop in that value. Occasionally, we put a more complex differentiable function in the bounds. For instance, in the upper bound here, we no longer just have an x. We have a more complex function. So let's see how this affects it. Affects the fundamental theorem of calculus. So as you might guess, you might be feeling a chain rule coming on here, since we're talking about nested function, and you would be right. So let's take a look at, let's come up with the antiderivative here. The antiderivative of cosine of t is sine of t. And we'll just check that. When we take the derivative of sine, we should get cosine. So we know that we can evaluate this at x squared, and we can subtract the value of the antiderivative at 1. So this ends up being sine of x squared minus sine of 1 radian. Sine of 1 radian is a constant. So if we end up taking the derivative of this function that we just found, which is the antiderivative here, that's like just taking the derivative of this function here. And if you notice, since we've substituted in the upper and lower bounds, we now have we're now being asked to take the derivative of a function that has a nested function inside. So here's where the chain rule comes in. Because we're being asked to take the derivative of that. The derivative of this, d dx sine of 1 radian is just a decimal, so this just equals 0. So what we end up then taking the derivative here is the derivative of sine is cosine. So we have the cosine of x squared, but then we also need to take the derivative of the inside function, which is x squared. So we have another 2x. So the derivative then of this definite integral ends up being 2x cosine x squared. So not only did we just retain the original function and plop in the upper bound, so here's our plop, but we also ended up with the derivative of our upper bound through the chain rule. So we can still use the fundamental theorem of calculus part 1 here, but with a more complicated function, we end up needing to use that chain rule. Now, just kind of an aside here, if we would go back to taking the derivative on the other page, we took the derivative from 1 to just x of cosine t dt. And we were being asked to take the derivative of that. And we ended up with just cosine x. We could do the chain rule on that. We could do the antiderivative here with respect to t as sine of t. We could do this the long way and say, well, that's like taking the derivative with respect to x of sine of t minus sine of 1. And that's how you get your cosine back. Excuse me, that should be x. So taking the derivative of sine of x is just cosine of x there. And then we could say that, we could use a chain rule and say, well, the derivative, the inside function is x, and the derivative of x is just 1. So we could use a chain rule here. It's just that when you use a chain rule on the function just x, the derivative of that ends up just being 1. So we actually do use a chain rule, we just don't really talk too much about it. So at this point, you should be able to know enough to start the homework for 5.4 day 1.